everybody, and welcome. My name's Joe Blue. I'm a data scientist with MapR. That name, if it sounds made up, I get that a lot. As far as I know, it's not. Anyway, you can reach me at jblue at MapR, JoeBlueMS on Twitter. Today, what I want to talk to you about is the secrets of the universe. And in order to do that, it's a pretty tough thing to cover that in a half an hour. So we might have a minute left for questions, might not. So see how that goes. What I'll try to do is interject some frequently asked questions where I think it might be appropriate. So anyway, the secrets of the universe, and I didn't know there were going to be so many people here. I didn't bring enough math for everybody, so you might end up having to share. But if there's any questions after, you can always contact me. So what I want to talk to you about is, so the secrets of the universe. The universe is pretty cagey. It hides the things that are really important, but the balance is that it leaves you little clues, and machine learning is just finding those clues and using them to create value. So the trick is how to take that value, or to realize that value, you need to actually do something with it. And so that's what I wanted to talk to you about today. First, how do we figure out what people are going to do? Those are the so-called secrets of the universe. Why do people behave the way they do? And if we could leverage that, we could build something that would allow us to figure that out. That's the machine learning piece. But if we think about it backwards, we can tee it up as a big fat curveball for search to deploy this. So you can end up building something very interesting without the resources of a massive company and the budget and the engineers and the data scientists. Which leaves you more time to focus on your data. So we're going to show you this couple of steps how to do this, and then at the end, how thinking about your data will improve your performance. So, and by the way, the key to improving this particular thing that I'm going to show you lies in the difference between razor blades and Citizen Kane. So if you want to figure out, or that's a teaser, if you want to know why that is important, you have to stick around to the end. Okay, so the idea is recommendation engines. We've been talking about them a lot. I think every presenter so far that I've heard has mentioned recommendation engines. So frequently asked questions. I don't work for Netflix. Actually, somebody might work for Netflix. I know we have a couple Amazon people. Do I still need recommendations? Well, the idea of a recommendation is just the interaction between customers, people, users, and things, actions that they want to do. Purchases, looking at another website, and so on. It's a pretty ubiquitous business problem. Driving your business forward is increasing the interaction between your users and items, or your users and other users. So it's a pretty common problem. Frequently asked question, I'm not a machine learning expert, can I build a recommendation engine? Well, it helps, but you don't need to be necessarily a machine learning expert or have a team of PhD scientists and a big budget for a group of engineers to build this and deploy this. So in a real world budget, this is something that you too can do. Do we want, and frequently asked question number 2, do I have the ability to build a recommendation on the scale of Netflix or Amazon? I would say probably not. They have massive teams, massive budgets, and the idea is you don't need to build the ne plus ultra of recommendation engines. Complexity doesn't always necessarily turn into performance, especially at scale. So the idea is build a pretty good recommender, certainly not on the order of these examples. And of course, around this time of year, you get bombarded with recommendations. You'd like this, you'd like that. You bought this, you looked at this. So the idea here is that the idea of a recommendation engine is very applicable to many types of businesses. Not just recommends of things you would like, what about things that you might not like? And there's a connect the dots there to fraud detection, anomaly detection. Why do people act differently than we would expect? So there's an aspect to that as well. So what we want to do, this is a typical, the time here doesn't really matter, but it's about the scale. Typically, when you're on a budget, you want to deploy something, you spend a little time looking at your data. And then you spend a lot of time building the code. What are we going to do with the data? And then you've got to spend more time to deploy it. You've got to go through testing. You've got to go through development and production and so on, and move the code around, test it. So the idea is, what if we could simplify development and deploy into a relatively small time frame? So typically, development and deployment might take months to achieve. But what if we could really shrink that down into a pretty small window there? That would leave extra time for more data exploration. And we've seen it time and time again as a data scientist. I see it quite a bit. The key is usually, to a successful product, is understanding your data. The rest is just choices that you might make that might have a little bit, might get you from a 93% to a 94% in your performance, in your capabilities. But understanding your data has much bigger effect. And so what we want to do is create that ability to lengthen the amount of work you put into understanding your data so that deployment can be relatively quick. Okay, so now what we need to do is come up with a way to figure out what people want, which is really the whole ball game. So I've got some users here, Alice, Bob, and Charles, and they have expressed an interest in some items. Another frequently asked question, my customers don't rate things. In Netflix, you might say, this movie's a 5, this movie's a 1, and so on. I don't have that data, so what do I do? Well, in real life, numeric ratings are rarely available, but people tell you what they like and what they don't like by their actions. I mean, if you go to a website and you look at a book and you click on, I want to see more of this description. So that's information that's logged somewhere. That shows an expressed interest. And really, when people do rate things, a lot of people don't have time. A lot of people don't know what they like at the time you ask them. But their behavior always belies what's really going on. So I've got Amelia, and what I want to do is I want to figure out or predict what Amelia might like. So a bad guess, I think, would be a bicycle, because only Charles got a bicycle. So another guess, and of course, you might have millions of users and thousands of items. But so a bike maybe not be a good guess. A pony might be an interesting guess because everybody else got a pony. Turns out that's a pretty bad choice. It's very common in recommendation engines, and I'll show you why in a little bit. But if everybody likes something, then the interesting combinations of items, the interest of that common item related to other things is pretty bad. So when you're looking at music recommendation, the Beatles, and everybody thinks it's a great band, are actually really lousy when it comes to recommendation because everybody likes them, so everything's associated with them. So, the secrets of the universe are find the pairs of items that are interesting. So in this case, a puppy might be a better choice for Amelia because those are she likes an apple, and maybe an apple, the other two users, Alice and Bob, express the affinity somehow for an apple and a puppy. So maybe the puppy would be a good choice. So the idea here, obviously very simple, but generalizes to millions of items, millions of users, is that the interesting parts, the interesting things based on your preferences, what would I recommend to you, it's not always intuitive. So in this case, the pony's not a good idea. So what we need to do is we need to figure out a way to take all of our data and then decide, well, what are some interesting combinations of items? I should step back a second and mention two big main groups of recommendations engines, user-based and item-based. And it really depends on how you think your customers interact with the actions that they might want to take. For instance, I worked on a recommendation engine in the healthcare industry. And the idea there was that the comorbidities are probably not good indicators of other diseases. For instance, if somebody has leukemia, it doesn't matter that leukemia is often associated with high blood pressure. I'm just making up an example. there's a lot more going on than just complex comorbidities. So that would be more of a user-based. I have 40-year-old males with leukemia who also have these comorbidities. What else might this particular person with leukemia might be looking after? But here we have just items that people might consume. And so there may be some things that we can mine, combinations of the items. So for instance, if you like an apple, you might also like a puppy. And that's just based on your user interaction. All right, so we need to get to the machine learning part. So how we figure out who gets what. So I'm going to show 3 matrices. I mean, if you're not comfortable with matrix, you think of it as a table or a collection. I've got a user item history. So I've got, of course, millions of rows. Those are my users, and probably thousands of columns. Those might be my items. What I want to find out are the items that go together in a way that's significant, something that's meaningful. So what we have here is just who likes what item. From there, we take what's called the co-occurrence. So how often do these things go together? So like there's the apple and the puppy, and this is symmetric, so along the diagonal, it's flipped. So 2, puppy and apple, apple and puppy, it's both 2. Now the diagonal would represent somebody likes an apple, wants another apple, and that's a decision you have to make, and I'll get into that in a second. Of course, if you have one apple, you could definitely go for another one, or maybe it's like those muffins that they're serving out there. But if you have a pony, you probably don't want another pony, so that's something to think about, and that's that diagonal there you got to think about. So now we have, this is really important, we have how often these items co-occur. It's a really big deal, but we're not there yet. And you look at this, and this says, well, it's not obvious that the puppy and the apple go together. So what we need to do, and here's where the machine learning part comes in, is we need to derive that third part, which is the indicator. And that is the subset of all of the pairwise interactions that are significant. So how do we do that? And this is a very sparse matrix. So for instance, if you have 1,000 items, this matrix becomes 1,000 by 1,000. It's 1,000,000 cells. But it's symmetric, so it comes out to n choose 2, which is about half of 1,000,000, just off 1,000 items. So there's a lot of things we need to calculate to figure out which of those are going to be significant. So how do we get from the middle to this is what we really want, which is just a list of pairs of items that go together at a significant degree. So the idea is log likelihood. And this is kind of gets into the data scientist dilemma. So a lot of these things can be complicated, and a lot of times I'm talking to audiences that maybe have a varying degree or comfort level with math. So what I'm going to do is show it to you in a way that I think everybody can explain it. And I do have something to appease the math people too. And we have a lot of engineers in here, perfectly fine with math. So what we want to do is figure out which items go together. So you can think of it, and this is on an item-based recommendation. The blue field is my total number of users. So what I want to do is I want to take my items 2 at a time, and I want to go through every combination. So this is a good case for big data. Even if you have just 1,000 items, you're going to have to do 500,000 calculations. Plus, you're going to have to get that user data into a format that you can use. So the only thing you need to know to figure out log likelihood or to visualize log likelihood is that how big is my individual circle of my item? The bigger my circle, the more users have expressed an interest in that item. So you take the apple and the puppy. So the puppy is maybe a little bit more popular than the apple. Given those 2 items and the size of their circle, how much do the circles overlap? People are using items left and right. There's a lot of items out there, but we can at least get a sense of how much overlap we would expect. So 2 circles that are fairly small, and if people liked items randomly, 2 items that are very small would probably not have that much overlap if everything were random. But on the other hand, if they had a lot of overlap, that's significant. That means people generally like those 2 things together. So given that information, and I should mention the pony and the bicycle. So these are much more popular items because they're bigger circles, and they overlap just a little bit. So in this case, the apple and the puppy A lot of overlap, smaller circles, that's significant. The pony and the bicycle, big circles, little bit of overlap, probably not a big deal. And that's all there is to log likelihood. But of course, we can't have someone sitting here looking at circles to say yes or no, right? So we need a different way of looking at that. But the other thing I want to say, log likelihood, there's two sides to it. I can say these things overlap so much, so significantly, that I think these two are associated. I'm learning. This is the machine learning part of it. What about if circles are so big that they don't overlap at all? That's a way to look at anomaly detection. So you could use the same approach to find things that should go together a lot more, but don't. So that's an interesting little wrinkle, and that may be applicable to your business. Why are the Beatles a really bad band for recommendations? Because they're so popular, they take up half the users. And so you would expect a lot of interaction there. So that's why very popular items don't tend to be good at recommendations. All right, so we need a way to quantify this. So one way to look at this data is a contingency table for each pair of items. So up on the top, and this doesn't match the circles here, but it's a contingency table of all users. So in this case, there are 10,010 users. 10 like puppies, 10 like apples, and those 10 they each liked both. So that's a very small puppy and apple usage, but complete overlap. So that's possibly significant, we're not sure. And then on a different case, and so this is more like 102,013 users, and the numbers are just kind of for illustration. 1,013 people liked ponies and bikes, but only 13 liked both. So how do we know which of those is interesting? The answer is the log likelihood. I won't go into it. This is only math in this presentation. But essentially, this Greek letter mu on the bottom, that's how much we would expect them to overlap. And then we've got how much did we actually see in all of these cells, add it up, multiply by 2, and you get a number, something like that. So 14.3, the numbers really don't mean anything. Higher means more significant, though. So we can take this number and subtract it from 1, divide 1 minus 1 over this, and come up with a number from 0 to 1. And find the cutoff at which I think this is interesting. I'm going to fill this indicator matrix. And that is the piece that's going to be used to deploy the search engine. So here's the next step. So how are we going to deploy this? I have, through my log likelihood exercise, I have this indicator matrix of puppies and apples go together. So let's say I had a document for a puppy. The ID is T4, and we have some metadata here. I could create a new field that said, by the way, the other item that goes with this is, the code would be T1, for instance, apple. So now, whenever anyone issues a query saying, I like puppies, you could say, well, you might like apples too. So that's the key here is that you could add an indicator to the metadata of an item in a Solr collection. And now you've got a fully operational search engine designed to provide information like this. Query for item, return other item. And that's basically what Solr is built to deliver. And the really interesting part about this as well is that Solr is already installed on your systems. You don't need to deploy anything new. Solr already works with everything. Your IT team is already cool with that. There's no programming to build this capability. It already exists right now. So what might this look like? I have some example architecture here. You could use anything. This is built on a MapR cluster. I'm not here to praise MapR. I'm just here to deploy, right? So the first thing you might want to do, there's an offline piece and an online piece. So the box is the offline piece. I've got to take my items, the metadata, the ID, the description, any kind of website, whatever information that you need to point someone in the direction, right? So I don't think I need to talk about how to take item metadata and get it to a solar collection for this audience. So you might already have that. But anyway, that is something that's going to run occasionally. Every time a new item's added, an item has been updated, taken offline, whatever. Of course, this could be an item. It could be websites. It could be really any kind of something that can be consumed by your customers. So we would do that just whenever necessary. Of course, the bulk load would start it off, and then minor updates could happen. Next thing we want to do is we need to get user history. What different users have experienced or have expressed a preference in what items historically. And that's going to be the information that we use to build those matrices and come up with the puppy and apple indicator. So I have that here. You might want to take that raw log information through Pig into Mahout. Now Mahout, you probably are aware, it's an open source machine learning package, Apache Mahout. You could certainly use Spark. You could program a MapReduce job yourself. The idea is this indicator matrix, that's the key part, this co-occurrence matrix down to those subset of indicators needs to be parallelized, or depending on the size, but generally we're talking about very large data sets here. So we parallelize that co-occurrence to item similarity matrix. And the reason I use Mahout is that it already has a job for that. It has a recommendation library to it, and it's got a really good item similarity job. So the output of that is pretty raw. It's just 2 columns, well, 3 really. It's because I told it I only wanted to see a similarity above, say, 95, 96%. All I'm going to get is a list of item 1, item 2, and a similarity score. But I also get item 2, item 1 because it's reflective. That's something that you can certainly play with, but generally an apple begets a puppy and vice versa. But for your business and your items, that might not be the case. So anyway, for here, because I'm on MapR, I was able to use Python to just take that data, create a JSON file, and update the solar collection. And that is where all the information, that's where when somebody says, I like a puppy, I'm adding to a special indicator field, you might like an apple. And I'm doing that for millions of thousands, potentially millions of items. So now that I have the solar collection, and by the way, another frequently asked question, how often do I do that? It depends on the interactions and the speed of interactions between your users and how relevant recent information might be. So you certainly want a lot of interaction. But if that happens in a couple of weeks, then maybe that's sufficient. But depending on how quickly you compile that information, you might have to go back months to gather that much information. So the third part is we just hook up some sort of web application, and maybe this is something that you already have, and probably that is the case. A user comes in and it triggers an event to which a recommendation might be appropriate, and a query is sent to that solar collection. This user likes bicycles and puppies and apples. I'm going to return those queries from my index of those 3 items, and then I'm going to take those recommended or those indicator items and do a relevance sort in that. And the results are going to be presented back to the user at the speed of your search engine. It's basically real-time machine learning and very little deployment necessary. The other thing I want to add here is that out of the box, is this going to provide really good recommendations? It will, but it might not always fit your business. So of course, in step 3, you might have some logic you want to add, like this person has had an apple in the last week or something. Let's hold off on recommending that same item. Or just little business logic that you could add to reduce the bad recommendations, or something that people would refer to as spam. Okay, so this is an example of a working recommender that you probably all possess the skills to try out on your own. So the promise was we want to do better than the basic recommendation engine because now we have extra time. We have a framework. Now we have extra time to look at our data. So what I've shown so far is a pretty simplistic recommendation engine. it's treating all behaviors equal. So what happens is that items with opposite polarity come up with pretty bad recommendation engines because we're trying to figure out why people like the things they like, why they do the things they do. But sometimes those behaviors can be conflicting. So if you can think about your data and spend more time thinking about your data, you might make this framework a little bit more complex, but not that much. So here's the difference between razor blades and, well, I filled in Citizen Kane. But I was thinking about a movie that, like The Beatles, would be a bad recommendation engine, would be a bad item. I'm thinking maybe Shawshank Redemption, because I think in the old days it might have been The Godfather, but that's too old. I mean, my kids don't even know what that is. It's probably a good thing, I guess. How do people, say, interact with razor blades? When you view razor blades online, it's kind of just weird. It really doesn't, what kind of action might you take after viewing razor blades? I mean, maybe we should get the authorities involved in that. But on the other hand, if you purchase razor blades, that's a really good indicator that you're going to purchase some more down the road. And differentiating that with, say, the movie Citizen Kane, if I viewed the movie, view it in the term of a website, viewed that item, it's very likely that I might want to buy that item. But on the other hand, if I buy that item, I probably don't want to buy it again. So this is an example of the opposite polarity. So we need to figure out a way to take those different behaviors, and of course, you're experts on your business, or at least you have access to experts on your business and how people behave and how you might even just think people might act differently. That's a way to improve this general idea of teeing up this problem for a search engine. So back to my item in a document in a collection. So I've got a puppy, and what I might want to do is say, clicks are important and purchases are important indicators, but I want to separate them. So I have, this is just the example, the first example. I've got my 3 matrices, and remember, all I care about is getting to this indicator matrix. I forgot my laser pointer. So now I've got a purchase indicator of apples. But what I might want to do is take the clicks data, do the same thing, and now this is separate. The data all comes from one source. I have users and I have their behaviors on different items. But now I can separate it into a different set of matrices. And now I've come up with purchase indicators and click indicators. So when somebody comes, a new user says, well, here's my click history, and I've clicked on a puppy, but I've never bought a puppy, they might say, well, you might like a bicycle. But if I come through and say, well, I've purchased a puppy, well, then you might like an apple. And we can have different types of indicators expressing different kinds of behaviors. You could even have some of the reverse of this. If my similarity were too different there's not enough overlap, I could say, here are some anomaly indicators. This person likes 2 things that may suggest maybe it's a synthetic identity, maybe there's some fraud going on, and so on. So the idea is to take this, whatever behaviors you might think are interesting, and use this to deploy a really good recommendations engine, not the best of the best, but something very quickly and something that you can deploy very quickly. As I predicted, the secrets of the universe did not yield in 30 minutes or less, so I'm pretty much out of time. This is my information. I wanted to leave you with something, though, and hopefully these slides will be made available. There's an ebook. It's a quick read. You can read it while you're waiting at the jetway on the way home. On our website, just MapR ebooks is fine. It goes into a little bit more detail, written by our chief architect, who helped me a lot with this presentation. And there's some other stuff there. And if you want to just play around with the MapR sandbox, put it on your desktop. You can play around with, you can install the sandbox, get Solar going, and have fun. So, and I'll be around if you want to talk outside. I'm sorry I didn't have time for questions. Thanks.